Hello, welcome to this video on arc length. Alright, so let's say I have this really poorly drawn curve here, and my question is, how long is this curve? Just a quick note, it does not have to be poorly drawn. It can be very well drawn, and you can still do this. So I have this really arbitrary curve here, and I'm trying to find its arc length. So, like, it's what we call arc length. How long is this thing? So, like, if I have, some line segment right here, we can pretty easily tell the length. It's the distance between the 2 points, and we could use our Pythagorean theorem. And so it's pretty easy, it's pretty reasonable to say that we could approximate the arc length of this big curve by chopping it into smaller segments and adding up the line, or and adding up all the lengths of the lines. So we do this, and we say, well, there are a bunch of points in between here, so we cut it into a bunch of intervals. And on this, particular illustration, they're pretty arbitrary. But then you can say, well, what if? Well, I changed my color. What if we chopped it into even more pieces? What if we went here, and then to here, and then we got one here, and then we went there, and now to here, and to there, and one like there, and finally one to here. Well, pretty soon, this thing starts to look pretty darn close to our actual curve, and it gets more and more accurate as you add more points to it. And so what we're noticing here is that, the more points you add and the closer they get, the closer that the sum of the lengths of all these lines, which isn't all that difficult to find, gets to the actual length of the curve. And so it's kind of like a Riemann sum, except you're doing a bunch of little line segments. And we can find the length of each of those line segments by the Pythagorean theorem. So if you have some little bit of curve here, and we usually denote arc length as S, so the arc length of something is usually given as S. Arc length, that's worth writing down. S. It's given by S. Don't ask me why, because I don't know. But it's given by S. And so if we have two components, if I draw a little bit of a curve here, or it could look like this or something, or it could be, it could be like this as well. It could be, it could be concave the other way. But, pretend this is some random bit of curve. Don't think it has to look like this. And I want to find, the distance. I want to find the length of that thing. Well, we know that x squared plus y squared has to equal s squared. With that said, let's imagine this as a little change in y. It's a little change in x, delta x. This is a little change in y, delta y. And this is a little change in the length of our thing, depending on where you go. Now, if we take that delta x, that delta y, that delta s, if we take all of those towards 0, you could put a limit on there if you wanted to make it a little more formal, then that becomes dx, dy, and ds. A little change in x, a little change in y, a little change in our arc length. And so then we can write, the Pythagorean theorem still holds for these little tiny things, so then we can write this. That ds squared equals dx squared plus dy squared. Okay, so now what we have is like, if I take a tiny, tiny little infinitesimal segment, we blew this thing up right here, but in reality, it's just, a small part of this curve that's drawn here. And, it could be anything. It could be, like that, or it could be, steeper or shallower, or it could be almost flat. It could be vertical. Well, it couldn't be vertical, and you'll see why later. I'll come back to that. And so this relationship still holds. So what we can do now is we can say, okay, this seems a little bit arbitrary right now, but just for now, follow along that with the fact that everything we're doing is completely legal, and I'll later try to, as much as I can, justify, what's going on. Well, right now what I can say is that we're trying to find out what ds is. ds in terms of x. Because if we graph this curve, if we graph this curve, we want to be able to go through every x, and we're going to integrate. We're going to integrate through every single x on our interval that we're interested in finding the length over, and we're going to say, okay, at that little tiny interval, this is a little piece dx. So if we zoom into that little tiny interval, we see some bit of curve, and we see this, and we pretend that it's perfectly straight there. But remember, this is infinitely small. So theoretically, this infinitely small length is the same as this infinitely small length. So it's an approximation as these changes in the variables go to 0 and give us our dx, our dy, and our ds. And so we have dx here, we have dy here, and we have ds here. Well, we want to find out, once we find out all of the ds's, then we can integrate all of those ds's. We can say the integral, that's the really poorly drawn integral. Okay, we can integrate all the ds's. And that ds is a little bit of arc length. It's the little bit of that distance. So if we add them up over some interval, a to b perhaps, or that's just some arbitrary region of interest, that will give us our arc length. And so that's a great idea and all, but how do we do that in terms of if we're given a function? If this is f of x, how do we do this? If this is y equals f of x, how do we do this? And we basically want to be able to plug in all of our x's and know what our function f of x is, know what our function y is, and be able to get our arc length. So what we're doing here is we're rearranging stuff to solve for ds in a better way. So this particular step, we're just dividing by dx squared. And the results can be seen here. ds squared over dx squared equals 1 plus dy squared over dx squared, not to confuse with d squared y over dx squared, which is the second derivative of the function with respect to x. So this is not what we're doing here. This is the entire derivative squared. So what we have is dy dx whole squared. So you take the derivative and you square it. You're only taking one derivative, though. Okay, so he shows that here, and we're just taking the square root of both sides, and it's the exact same situation with this over here, where you're squaring the whole thing. It's not a second derivative. All right, so we have this, and once you take the square root, you have ds over dx. And let me back up for a sec, and take a moment to appreciate what this means. ds dx, that means per little unit dx, I can tell you what ds is, and that's great. It's like for every little bit of dx, we can tell you how ds, the change in arc length, and the dx are related to each other. And all we need to do now is shift this over and get ds is equal to the square root of 1 plus dy dx all squared, dx. And so this is exactly what we were looking for. This is our ds, and we have dx, and now we can integrate both sides. When you integrate ds, if you add up all the, remember, integrating is just adding up over some domain, a to b. If you add up all those little bits of s, ds, then you're going to get s. Makes enough sense. And here on this side, we're going to integrate from a to b, and we're just integrating this expression. And so we're looking at this with respect to x. For every little bit of x that we go over, how much do we have to add to our arc length? And that is the expression that gives us our arc length. And once you have that, I mean, honestly, understanding this is the most difficult part of it. And after you have this, this is a pretty, neat formula that you can just apply to certain things. But, don't use this if you don't get this. So going on, this is just, summing things up here. Arc length, S's arc length is integral from x equals a to b of the square root of 1 plus f prime of x squared, or dy dx squared. It's the exact same thing. And just on a side note, if you had some funky function that was, if you did have something that was a function of y perhaps, it would be y equals a to y equals b the square root of 1 plus dx dy squared, dy, which is kind of odd, but it's like if you had, instead of, y equals x squared, you had x equals y squared, then you could take the derivative of both sides with respect to y, and you would get dx dy equals 2y. And, that's how it would work out there. And so, you're probably not used to seeing dx dy, but it is legal, in fact. And if you're, looking at it like that, that's what you need to do. And so this is for a y direction. So if you have some graph perhaps, and it's something like this, where it's only a function, if you look at it this way, this passes a vertical line test, but this most certainly does not. So that's just a side note, and we're going to see this in action a few times. So find the arc length of the graph of the function over the indicated interval. The graph is y equals the square root of x, and the interval is from 1 to 4. So this little segment here has already been highlighted, and we're simply just plugging in. This is our formula. Now to find dy dx, that should be very easy at this point in your career. Y equals the square root of x, y equals x to the 1/2, and hence, if we take the derivative of both sides with respect to x, dy dx is just 1/2 x to the minus 1/2, which is exactly what's being put in here. And then we're integrating 1 plus that over that particular interval. This is probably a job for a calculator, but maybe it won't be awful. Maybe it will. Oh, so yeah, that's how he's leaving it. So usually you're just, on an AP test especially, you're just going to be either leaving it like this, or your calculator is going to do the work for you, because integrals like that can often be nasty. Okay, find the perimeter of the shaded region in terms of k. This sounds AP-ish. All right, what's going on here? So we've got this region, and it looks like x equals k. So what this is telling us is that this is variable. Like, this is saying, if I give you a k, you should be able to give me the perimeter. So what we're really looking for is the perimeter as a function of k. So this, k could be here, k could be here, k could be here. It does not necessarily need to be here. But in light of that, we still need to be able to find the perimeter of it. So the perimeter of it, it's going to be the arc length here, plus this thing, plus that thing. Easy enough, right? All right, so this is just labeling some stuff up. The points here, 0, 1. This is k1, wherever that may be. It could be here, it could be here. And this is k, and 1 plus the square root of k. So you're plugging in k for your value of x. Okay, just putting in the formula here, and we're just maintaining that same formula. Oh, and the other thing is that, the arc length from 0 to k of 1 plus square root of x squared is exactly the same as, it would be on this one, because the inside, this dy dx is the same, because when you take the derivative of the constant, it just disappears. So you could shift this up as much as you want, or as down as much as you want, and that makes a lot of sense, too. The length of a function shouldn't depend on where it's sitting in space. I mean, I'd be very scared if the, math said it did. So we should, take solace in the fact that that does match what we're thinking. Okay, so we're going from 0 to k, which makes sense. That's our x interval that we're looking at the arc length over. And so just plugging this in, doing the squaring, and simplifying that a bit, that's the integral. So that gives us this portion over here. And what we're looking for is that. Okay, so we're separating this into several different regions. And that is this part, which is given by this. That's the curvy part. But the other ones are just lines. So this distance right here is k. That makes enough sense. So that one's here. And this distance right here is proportional to the square root of k. If I plug in, if k is 4, then this length here is going to be just the, that length is going to be the square root of 4, which is 2. If it's 9, it's going to be 3. And so you've got that proportionality there as well. And so in its entirety, this gives you the perimeter of the entire expression. And those were practice problems assigned on the day that Mr. Kalis was not here. And you should do those after watching the video. Maybe you tried, maybe it was an epic failure. Hopefully not, but if so, hopefully watching that video cleared things up, and have a nice day.